So my name is Schelle. I recently got my PhD at the University of Colorado, and my previous work was more scheduling across heterogeneous processing resources. So you could imagine not really quad-core processors, or maybe the fusion style of processors. And so what I'm currently doing is I continued on as a postdoc at the University of Colorado, and this is kind of the project that I was kept on to work on, and the whole idea being similar to things maybe that are going on at WINLAB is that we're trying to look at how to manage resources for these software-defined radio applications. And what I specifically do is work on the FPGA side of things due to I've worked with the Xilinx research labs for a while, and so I was kept on to push to the final push for this project, which I'll try and talk about. And that'll be the focus of my talk, is the FPGA side. So with that said, the overview of the talk, for me, just trying to think about this group and what you guys would be interested in hearing about, looking at the platforms that exist and whether software or reconfigurable computing is the correct platform to begin with, or some combination of the two. And I'll focus on the FPGAs specifically, focusing on the architectures and tool flows. How, of course, we're all aware that FPGAs can give you some nice performance as you can create your own circuit, but looking at how the tool flows actually make that usable, since sometimes they can be difficult to actually put designs on. And then at the University of Colorado, I'll focus on our FPGA general purpose processor platform. Really look at the hardware that's on top of the FPGA. Again, focusing on that side of things, and look at the project flow so far. And at this stage, look at the preliminary results at each step, just trying to show you what challenges we've come across, how we've solved them, and how we've gotten to the platform we're at today. And I'll just give conclusions on that process. So with this group, probably don't really need to go to what a software-unified radio is, but Wikipedia is always a good start. And it's just the ability to tune the frequency band and any modulation across the frequency spectrums with, and I want to focus on as little hardware as possible and processing the signals through software. And what I, as an architect and a researcher, just get out of it is that it's a new application domain that has high throughput and high configurability, which is what I'm interested in as a researcher. Not so much what happens, it's just that those two requirements. So with that said, you have things like, this is just kind of a transmitter flow for an 802.11 transmitter, and it's nicely decomposed. It has nice interfaces. It's very simple to just push samples through. And what you can get with the software-defined radios, you start having the idea that, okay, well, I need to switch out various modulations. Maybe the transforms at the last step you can do in a variety of ways. But at the end, you always have to have 80 megasamples a second pushing out of the system. And typically, these two constraints are a trade-off. You switch one for the other. You don't really get both as with radio designs. Typically, it's hardware for the sole reason that I don't care so much about configurability. I just want the thing to work. And so when looking at that, the decomposition of what you need, looking at those throughput and performance, it's the idea that you can program it so that when new modulation schemes or frequency hopping decisions are needed, it's easy to program. And the flexibility, of course, is that it's easy to switch things out statically so that I can design new modulation schemes and drop it in the system. And of course, moving that further along to runtime, you need it to be reconfigurable, whether it's a general purpose processor. When I talk about reconfigurability, it's switching the instruction pointer to a whole new scheme using various pointer systems and various classes and cores like that. But then you get to the performance side, and I focus on sample rate just because that's what we look at as our metric of success. And then there's also performance, which of course could mean anything. But when I look at that, it's kind of the computational performance, whether it's good at control flow, which processors are typically good at, or whether it's good at bit level operations. As you get closer to the PHY, you need to do a lot of bit operations, which general purpose processors are terrible at. But so the performance can be almost anything, but sample rate is what we focus on for our project. So looking at the kind of de facto software general purpose processor project that we look at a lot is GNU Radio, and hopefully people are familiar with that. But again, it's just a C++ environment. People can design libraries for a software world. And it has all the things you expect with software. It has programmability, flexibility, reconfigurability. All you have to really call is the work function on any core, and it'll work. But the sample rate is typically I/O bound on the general purpose processors, and the performance on very low level computations, once you get very close to the PHY, is very poor compared to ASIC designs. And so when we were first looking at this, just to quantify it a little more, as we started looking at the I/O bound, what can we get into a general purpose processor? And we started looking at the interfaces, and we look at the mega samples per second that we could really pull from USB, PCI, gigabit Ethernet. It's only once we start getting to the PCI Express that we start seeing really good mega samples per second that can cross the channel. But a lot of our first designs use PCI, and we thought, well, if we have a dedicated PCI bus, then we can really push some samples through because it'll be a point-to-point link. But the PCI bus standard has a very large arbitration lag between. You can get about 1,000 samples across, but then it has a big lag for arbitration, even if there's only one person using the bus. And so we moved kind of down the chain. Then you see a PCI Express with 16 lanes. You can get 1,000 mega samples, but you don't see a lot of 16-lane PCI Express cards available, or you don't see a lot of slots in your computers right now. And so we're waiting for that mega samples a second, which of course is it really defines the sample rate, but it doesn't solve the performance problem. So we started there, and then we looked at FPGA solutions, which kind of like the Rice Warp project is another one. The work here at WINLAB is another one. The current CU, the University of Colorado I work on, are similar. Programmability, flexibility, reconfigurability. You can say they're there, but it's still very difficult to find FPGA programmers at large. But of course, you get the sample rate and you get the bit level performance that you need because you define the circuit. So if it doesn't work, a lot of times it's the designer's fault. But with that said, you can change these to a positive if you know how to program FPGAs. And a lot of us think what I hear is that FPGAs are the worst. But reading through some WINLAB technical reports, there was a decision to avoid the use of DSPs with the difficulty associated with programming these devices. And so we decided to use a combination of FPGA for hardware implementation. So it goes to show that people make decisions based upon ease of programmability. And this group here went with an FPGA solution because DSPs, perhaps there wasn't the knowledge, perhaps it was too hard to get them. But FPGAs can still be considered very difficult to program, and I say that, but I feel very comfortable programming FPGAs. But to get widespread of adoption of something, it sometimes can be very difficult. And so, with that said, it's kind of what makes FPGA so difficult to program in a general sense, not focusing on Marco software-defined radio platforms. I worked with Marco at the University of Colorado, So what makes FPGAs difficult for doing this kind of research, for creating a software-defined radio platform that's usable by everyone? You look at FPGAs, and before 2002, all you really got with an FPGA was some reconfigurable logic. So you could create pretty close to the transistor level, but slightly above it. But it was really a homogeneous sea of transistors. And nowadays, for better or for worse, you have a variety of components that make up an FPGA. What they've started doing, of course, is to target certain markets. The FPGA, the industry has started embedding cores onto the sea of reconfigurable logic to target it's really to target markets. And so when they put on a DSP resource, it's the FPGA community saying, oh, all our customers are using this signal processing core. Why don't we just embed it in there and make it faster? So they start doing things like DSP. The high-speed off-chip links will have, they'll have multiple gigabit transceivers embedded in the FPGAs for the sole reason that Cisco is like, for Xilinx, that's who I can speak to, because Cisco is a huge consumer of FPGAs. So they're gonna give Cisco these high-speed serial links. But then they started embedding distributed memory, and for some reason the memory will match the size of a jumbo-sized Ethernet frame. It's just that FPGAs, when they start embedding all this stuff, it really becomes a heterogeneous, coarse-grained processing platform. It's no longer logic, which is great for performance, but for configurability, it becomes a challenge. And so, again, just trying to focus on these programmability issues of FPGAs. It's a large design space. It was a large design space to begin with, but now it's great for small team projects. But for widespread adoption, you begin to become focused on one provider of FPGAs, a Xilinx or an Altera or the other ones. But you get tied to an architecture and a generation of FPGAs. So if I gave you a Xilinx Vertex FPGA, and then I gave you a Xilinx Vertex 5, which is multiple generations away, oftentimes you can't port the code over. And this becomes a huge problem for designers who say, I want my design to work on anything. And in the software world, analogously in the software world, you have GCC that will mask away whatever architecture you're working on. And typically there's a lot of people that work very hard to make sure that software works across platforms. It's not always the case with FPGAs. So with that said, the embedded components, as I said, lead to the higher performance, memory bandwidth, I/O speeds, transistor density. But what about the configurability, which is, of course, extremely important for software-defined radio? And in many application domains, the way the FPGA providers do this is they do tool flows to hide the complexity of this programming. And this is extremely important for using FPGAs for software-defined radio. The perennial examples are the system generator for DSP, which is what, at University of Colorado, that's what we use to design for our FPGA for these signal processing applications. Some of you may be familiar with the EDK. It's another tool flow that's good for processor designs. And I mentioned the last two because they're mine, and because it was part of my work at Xilinx, and hopefully you'll see it in a product soon. But it's for networking, and the same thing for packet processing, which some of you, part of the WINLAB is the platform is a packet processing FPGA, and I'd be very interested to hear what tools you're using with Lucent. But really, what do these tool flows do? How do you make FPGAs usable if you're going through this tool flow model? And every FPGA tool flow does three things. It masks away libraries of pre-generated IP. And if you've ever used the tool flows, you know what I'm talking about. It's block diagrams. It's drawing things together, connecting them with wires or buses, which leads to the second point. They provide the glue interconnect to these IP. So if you put a soft processor onto an FPGA, just out of reconfigurable logic, you can drop on these nice little processors that have all the nice compiler tools with them. What they do is they provide the glue interconnect. They provide the bus standards for you to connect things to, so that you don't have to worry about it. And the last one, which is interesting in terms of software-defined radio, is that they create static circuits. And leading to the next point, well, it's really difficult to pre-generate IP for a dynamic application onto a static FPGA. And the solution that we target is replacing the static circuits with runtime support for switching out the circuit itself. And I'll talk about partial reconfiguration as part of that solution. But back to this being software-defined radio, it's really interesting because there aren't a lot of domains that demand this kind of runtime support for FPGAs. And there's not, most of them are just drop the circuit on and it will work, and it will beat, it'll give us a great time to market to put this on an FPGA without having to go and fabricate it. but no one who really uses FPGAs will want a dynamic application. There's various reasons why you would want one, but I think software-defined radio is, I believe, one of the first ones that I believe in that will make FPGAs a great solution for a general purpose processing.
What is the time it takes to reconfigure?
It can be, it depends. So on an FPGA, it really depends on the size of the FPGA. So it can be on the order from 1 to 100 milliseconds. And I'll talk about that a little bit more, but you're right. To swap out circuits onto an FPGA at runtime, there's various work that looks at partial reconfiguration, which is taking a percentage of the FPGA, swapping it out at runtime, and it's a set interface, it's a set timing. You figure out how big your circuit is, and then you can do the math to figure out how long it'll take to reconfigure. It's very deterministic. So hopefully, I've convinced you that tool flows are a great way to use FPGAs. Pre-compiled IP is a great way. So that of a way to get something accepted and used in the community. And so with our architecture, again, looking at a general purpose processor with an FPGA with an RF front end, and there's 3 components to this, and I'm sure people in the room are interested in each. The general purpose processor, we use whatever we buy. That's not a concern to us because it's always going to run slow. But the RF front end we had made for us by Fidelity Comtech, and it's a tunable, just a general purpose. It gives us 802.11 functionality. And I'll admit I'm not too familiar with its inner workings, but we just bought it and it plugged it in and it worked. But and then we have the part that I'm interested in, of course, as hopefully you can guess, is the FPGA, which is a Nalitech Extreme DSP board. Costs a couple $1,000. But this whole system, the goal of this whole system was to kind of make it cheap. So when the funding for this project came up, there was a variety of solutions. One was give us a $100,000 plus solution. One was give us a $5,000 solution. One was give just a library of components. And so this is kind of the low-end solution to the problem of making software-defined radio platforms. And you look at, again, looking at the things I said that an FPGA tool flow needs to be accepted and used in the community, the runtime support, the interconnect, the glue logic that I talked about, and the pre-configured IP, we have all 3 of those. The runtime support, the end goal is to have it run on the general purpose processor. Right now, part of my thesis was doing it on the FPGA. But we've attached that GNU radio front end to it as well, which I will admit is slow and we don't use it, or I don't use it because I focus on the FPGA side of things. But it's there. We have that interface there as part of the system so that if you wanted to have something run in software, you could. And this is kind of the project flow that we've come to. Everything on the left side is kind of what I've taken on and are personally doing, and it looks like a lot compared to the right side. But the ones on the right side, if you know, can be really complicated to do in themselves. What we've done is I'll talk about the concept of a network on chip interconnect that gives you that general purpose glue logic that I was talking about that you need for these kind of systems. The operating system is that runtime support, again, to make it usable. And then as we move through, then it becomes application and software-defined radio specific. A colleague did the Handcrafted. It's an 802.11 transmitter. We were able to see it on a laptop be received. GNU radio with an FPGA front end, and I'll talk about that, though it's not my work. And then taking this 802.11 transmitter, putting it on the FPGA in a general purpose way. I presented that at FPL, which is an FPGA conference in August. And then it becomes kind of what I've done for my postdoc work, is taking the transmitter and partially reconfiguring it over a network on chip. So we were mentioning before the partial reconfiguration. I'll talk about that a little more. And then the receiver, 802.11 receiver, which again some of you may know is much more complicated than the transmitter. has much more control flow. That's almost done. We're seeing packets come through, and it's about to be completed. But once I get a finished version, again, reconfigured over the network on chip, and then publish our various results. And the project is supposed to end this semester. And so what I'll focus on is kind of I really want to focus on the things that have been done, which you know, as an audience member may be terrible because you'll want to see the final results. But I really, since there's so much similarity between the WINLAB project and our project in a variety of ways, that focus on the things that have been done and talk about. We're pretty sure we know how to do this last step. It's going to take me a couple months just to make it work. But I just really want to go through these various parts of the project and see what you guys think about that. So that's the order I'll kind of go through, just to give it, you know, the order of things to talk about. So to step back, kind of just from, you know, the software-defined radio aspect, we're looking at part of my thesis was to make this FPGA-based network on chip. In some discussions earlier today, what is a network on chip? The short answer is, as processors or any system on a chip moves to multi-core to many-core, which is now the buzzword. I've heard multi-core being 2 to 4 and many-core being 8 to 1,000. Instead of using the bus for on-chip communication, you start using a packet switch network built onto the chip. And the reason being is that, as we all know, buses don't scale well to these high count of access points. So and for a software-defined radio specifically, you need a scalable interconnect. You need, you know, whatever your processing tile is, whatever you're doing your transform communicating to a modulation scheme, you're always going to have streaming data. That's always going to be the flow. You're going to have a very high streaming data rate. And so you can just imagine, just think in your mind of using a bus when you have maybe your task graph has 10 access points, and they're all communicating over a single bus. They all get 1/10 the access time. So then you can imagine how slow a streaming application will work in such a system. So a network on chip allows you to isolate communication. You can create virtual point-to-point links, various things depending on how you implement the network on chip. But it's very appropriate for a data flow application. With that said, part of the work, you guys can actually find this online if you'd like. Opencores.org. We put this up there in April, and I still get good emails about it from people, various groups around the world using it. But it's a synthesizable network on chip. And when I say synthesizable, it means you could drop it onto an FPGA, put it in a product, and it would work. As opposed to simulation-based, which is what you see a lot of times. You see these great results, and you ask them for hardware, and it doesn't exist. But what it does, in a general sense, it provides a glue interconnect for IP blocks. And that's, as I said, that's very important for these kind of systems. And specifically when you're targeting a data flow application, the buses that you can receive, the IP buses, just won't work on for this kind of application. So the next step, if you believe that the network on chip actually exists, is the runtime support. And this was another part of my PhD thesis. Runtime support for applications running on network on chips is kind of a new thing because there aren't a lot of actual pieces of hardware that exist that had a network on chip that you could easily get. And this was kind of when I started the thesis several years back. There were no parts that had network on chips that you could get to. And nowadays you're starting to see them pop up more and more as more cores are placed on single dies. And to give runtime support for network on chips, we really looked at scheduling, partial reconfiguration management, which I'll talk about, but it's the idea of if I split my FPGA up into 30 parts, how do you go about reconfiguring part of it, pulling it out, and putting something else on there, and doing it in a way that doesn't it doesn't destroy your chip, but it will. It's a non-deterministic state kind of problem when you switch out circuits and pull them in and put them out. You get some interesting behavior. But then also part of this was profiling application behavior, which isn't too necessary for software-defined radio, but it was necessary for the thesis work. And as part of this operating system for the chip, everything we did was on chip. Everything we did was on the FPGA. So for a software-defined radio application, it would have some tiles that would do various radio processing, but it would also have a tile on there that would be a processor running Linux or running something else on it to do this kind of work and manage the chip. And so this is kind of what it looks like when you're, just imagine on the right you have your FPGA kind of configured to, you put a circuit on there to do the network on chip, and you've connected a variety of things, which may be software-defined radio tiles. And then as you connect to a processor, you just see a kind of a general purpose just scheduler like you'd see in any kind of OS with scheduler events, only that it was allocating and pulling the NOC for various information. And so it's just a general purpose slide I nicely was able to pull out of my defense slides. But what does this mean? So what does this kind of mean for like what the size of things? And the reason I bring up the size and the reason it's important for FPGA work is if you want to put Linux onto an FPGA, you need off-chip memory. And that's only interesting if you have a platform that doesn't have off-chip memory. And oftentimes, if you had a handset or something else, you may not have the memory system connected to the FPGA. So if you really want Linux on FPGA, the UC Linux, which is one of the smaller embedded Linux, it's 2 megabytes for a full-blown kernel, embedded kernel, versus a standalone, which is 32 kilobytes. But with the high Linux overhead, you get really nice file system and network support. And as we're talking about software-defined radio, having file systems and having network support might be a really nice thing. And so it's always a design trade-off that we've typically gone with a standalone version for the sole reason it runs much faster. And that's what the graph is showing on the right, is that depending on the bottom axis, if you can't read it, it's just the number of nodes on the network on chip, and then that's decision time. So you can see that as you get more nodes on the chip, in order to make a decision on where to place things, the Linux version starts taking a very long time, which is, a terrible thing if you have a very tightly bound radio application that you've placed on this system.
So this is simulation-based results, right?
Yes, it is very much so. We're able, the graph goes up to 250 nodes. Well, this isn't actually, this isn't two simulations because it's all run in software. So I can run it, but it actually doesn't make the decision because the hardware could never fit that many nodes. So but you're right, it's the time it takes to make a decision, and but in light of the fact that I could never fit 250 nodes on a FPGA, current FPGA technology, then you're right, it is never realized in hardware.
So the time is actually measured on the real hardware, but then you extrapolate it.
Yes. Very, yep, that's correct. But with the operating system for a network on chip, this is kind of one of my fun graphs. It was enjoyable to make because it's so weird. But this is the utilization of a network on chip, and you can imagine a grid of processors where these are the ones on the corners of this graph are the corners of the mesh. And you would always imagine with a network, it's very difficult to get uniform traffic patterns on a network on chip, because you imagine with deterministic routing, which is often used for simplicity, that most of the traffic moves through the center of the network. And there's various misrouting schemes you can use. But the solution we came to is if you want to move it over to where you have very low utilization, very uniform, just have your operating system make better decisions. And if you're scheduling better, you get better utilization of the network on chip. And better utilization usually leads to better performance since there's not contention. And this is something you could never really do with a bus, where everyone accessing the bus is typically an equal accessor to the bus. You'd see everyone uniformly bad. And this is showing that with a network on chip, everyone's uniformly getting equal access to the system. So if I've convinced you that a network on chip is good for software-defined radio and that an operating system using the network on chip is a good idea for software-defined radio, we took a real working example We took an 802.11g transmitter, and that's what the graph is on the right. If you're familiar with System Generator for DSP, a Xilinx MATLAB tool, you can make a nice block diagram, and then it'll create a circuit that you can put on the FPGA to run. And so what we did is, taking those two parts, we put GNU radio, and using this Xilinx, the Extreme DSP board, it gives you a nice PCI bus interface. And as I mentioned before, PCI bus is terrible for streaming data across, but it's what we had at the time. This is about the results were published a year ago, I would imagine. So, but we're continually using it. But it gives you an example of what you can do. So with that in mind, it was the work of, give credit to where it's due, Jeff Fifield and Dirk Grunwald. Dirk is also my advisor. But the FPGA, just using an FPGA, making a handcrafted circuit, no NOC, no OS, you can get the 80 megasamples a second. So it's good to see that the FPGA can achieve it. But what happens is, once you hit the PCI, like I was talking, to do anything else, to use a GNU radio, maybe use some of their processing, it creates a large bottleneck. And what happened is, when Jeff was working on it and I was helping him with the FPGA side, is that everything eventually was getting just pushed onto the FPGA, because that's where all the work could be done in a timely manner. And he eventually just had some very low-level control on the general purpose processor. When I say control, I mean changing the modulation scheme, so sending that across in the system. And for the sole reason that, if you've worked with FPGAs, doing control kind of on FPGAs, making decisions that processors are good at, you kind of end up with a processor, because it's just better. It's better described in a C language than in Verilog or VHDL. But it was configurable in some characteristics, and all this was done in software and pushed onto the FPGA.
So what
Yes.
is the GNU radio part? When you say GNU radio, what do you mean by that?
In that specific project?
Yeah.
Well, in that specific project, it was the same composition of parts. You know, you do the error correction, then the modulation, then the transform, and then you push it out on the wire. And what Jeff did on that work was look at, as you moved this task graph, it's a very straight pipeline. The transmitter, as you moved from software onto hardware, looking at each of the interfaces and saying, you know, I get this result, I get this performance by having this half of it on software with a GNU radio block. So with the, for example, with the Fourier transform, or I'm sorry, with the transform part, GNU radio has a block that will do that for you. And I mean, you can find them anywhere in software, but of course it's terribly slow. And so he'd say, all right, here's a GNU radio version, here's how fast it ran, here's the one on the FPGA. And it was just that, it was the ability to move it. And it was a master's thesis, and he kind of, you know, it was
like comparison analysis.
Yeah, and the difficulties that he had in moving things across, and then it really came down to the PCI bus, and we kind of had to plug onto the bus and say, why is this not streaming data? Because you could do DMA.
Right.
It had a DMA interface on the FPGA, but it was just the bus, and we had nothing else plugged onto the bus. And so we just kind of threw our hands up and said, well, it had a terrible arbitration lag, and there was nothing you could do about it. But yeah. So the next step, as we move along, is taking the NoCem tool, that emulation, and partitioning the FPGA architecture onto a network on chip. In this work, this was the one I was talking about at FPL, and that was just last August. That's why I keep saying it, but it was so recent. But it got you look at the. It's not too hard to partition this design, because what we were doing is we left all the error correction code and the framing kind of work. We left that on the general purpose processor. We just kind of focused on this FPGA part of it, and the modulation and the inverse transform, and then the sync work of inserting guards into the signal and things like that. We kind of looked at that, and it lent itself really nicely to an FPGA, because you have things where you have I/O I/O ports, which, as I was mentioning, FPGAs have now these nice I/O interfaces, or they're extremely fast. You have modulation, which is a very low-level, bit-level lookup. It would take a while to do on a processor, but on an FPGA, it's very much single-cycle work. And then you have the transform, which is very interesting. We tried to do it in software. We did an embedded core on the FPGA, an embedded processor on the FPGA, and then we have a dedicated hardware. And the transforms, they take up a lot of space on FPGAs. It's just the work that goes into doing them and spitting out the results in order. It takes up a lot of space. So you have a very small modulation block. You have a generated IP core on the transform. Then you have another I/O sink. And so it lends itself to the FPGA architecture due to the variety of needs you have. And so this is kind of an example of what it would look like if you partitioned out the NOC in such a way. Depending on, the source and sink would probably be well predefined, but the modulation and transform you could move around depending on your system if you were able to do such a thing. Just to show you what that simple example looks like. And we were able to get 50 megasamples a second, so we didn't achieve the 80 megasamples we wanted. And it was basically because of the clock rate we had, we were only able to get with a handshaking with FIFOs. It was only the handshaking with FIFOs, and we wanted to keep the network on chip as set in place as possible. So we just reported those results, and we gave it that it had reusable software-defined radio components that could be swapped in and out, and the performance was really affected by placement. Again, just lending itself to the fact that an operating system managing the part is a lot more important than it is with a bus system. So, if you're still with me, the 802.11, and this is the 802.11 transmitter, we partially reconfigured over network on chip. And if you're not familiar with partial reconfiguration, it's kind of like what we were talking about earlier, is the fact that you swap in a circuit, you define a region of your FPGA, a region of the real estate, as partially reconfigurable, and then you're able to create some various macros that you put in there that tell the tools that it's partially reconfigurable, and then you're able to create circuits for it, as many circuits as you want, and then you can drop them in using various hardware constructs to do it. But it is still challenging because the tool flows are very experimental. If you've ever tried to get the tool flow, they kind of like to know what you're doing with it, and it requires another set of Xilinx tools that are usually very expensive, the plan ahead tools. It's very complicated. It's very much, you don't want to mess it up. You just kind of do it right the first time and then run a test, see that it works, and you kind of walk away. But it's challenging for people like us because it also increases an already large design space. You already have the various ways of using IP, using these embedded cores, using the logic. Now you have more FPGA than you originally did because you can swap in new circuits. And then it also adds to your design because you have this various control for bitstreams, which I'll talk about, and you have to enable and disable parts of the circuit. But to do the bitstream manipulation, the typically way you do is you need a file system, you need the bits already in place, and then you have to add some pieces of hardware into the logic as well to be able to control it. Or you can do it off chip using JTAG. And so it just adds to this, like, do I really need to do this kind of question. And so, but there are benefits, and though a large concern with FPGAs is, in computer science we deal with the number 0, 1, or infinity. If you can, I should be able to virtualize everything on an FPGA, and I don't like it when I run out of space. And it's kind of like with software, I should be able to put, I should have a virtual table, I should have virtual pages, I should be able to run as many threads as possible, and all these good things that when I think of computer science, this is where FPGAs fails. Once I run out of resources, it's done. And so the benefits is the virtualizing of the FPGA resources is a really important thing for FPGAs to be accepted in general. And for software-defined radio, it really does enable the dynamic IP placement that before you couldn't do. and it allows kind of a library-based system where I create libraries of components that I can drop in at runtime. And of course, it's almost guaranteed publications. At least in the FPGA community, there's always a section, or if it's not the emphasis of the entire conference, is the ability to use partial reconfiguration to do anything. And so people really like it these days.
So,
Questions? Yeah.
Is having something like a NoC a requirement in order to be able to do this?
No, not at all. Oftentimes you use a bus. You always have to have a way to disable the interface to that block, and so it's one of these things where that's all you need.
You have to start out with something which is at least a well-defined bus, and that has to be the only interface to the block.
Yes, because what happens is when you do a partial reconfiguration, if you have control bits coming in and out of it, they toggle like mad, and so you don't know what's going to happen. So you have to disable those.
Well, I'm asking because we tried to do something much simpler, but something that required an incremental placement out on a Xilinx FPGA, and
yes,
it just didn't work out at all. The incremental part basically failed, or you used up so many resources over a full resynthesis that it didn't make any sense.
Yeah. Well,
you're obviously here going well beyond just a simple incremental placement.
Yeah. Maybe we should talk about it afterwards. But you're right. I mean, it is one of those things that is extremely difficult, and I would never claim to be an expert on it, but the times we've done it, you really have to be careful. And then there's very interesting things. Something I don't mention is standard VHDL won't work. If you drop in a new circuit, you have to initialize everything, and sometimes you assume, in the C world, sometimes you often assume that things are set to 0 when they're not, when they're a garbage value. And I've had that problem. I had state machines that I'd drop on a circuit, and the state machine would think it was somewhere else, and that was part of the state, and it would be haywire. And so there's various. It's just these really minutia things that you take for granted that when you're doing swapping in and out circuits that cause problems, and I'd love to talk about it more.
So I have a question.
Yes.
So you have multiple tiles, right? So
yes.
Are they all symmetric in the sense that you can drop one synthesized design into any of the tiles?
The short answer is no, because you're right. Because I'll talk. Actually, I think it's the next slide. I'll answer your question. Just one more slide. So we took the transmitter and we partially reconfigured over a NoC. And you can notice, if you're familiar with the Planet tools, you see two very large sizes. You can imagine which one's the modulation and which one's the transform, hopefully. And if you did, you're right. Because the thing is, you're correct that the symmetry of them all it's always a battle in the FPGA community about kind of using, it's almost like page tables, or it's using paging or segments. Segments to match the exact size, paging a general purpose solution. And so I guess we kind of take the segment approach in that for right now, because we're just happy to get it working. Because it is really difficult, is that the transform, you can see how much bigger it is, and the transform in sheer size alone is 80 times bigger than the modulation scheme. So to page it out would be a challenge for us, because we'd have to take the biggest or do a much more complex piece of work to swap things out. And there's projects out there that they'll have an interconnect in place, and they'll allow you to group two blocks together to make bigger parts. But then it gets a lot of that work that you see, oftentimes you don't really get the full picture, and then you ask them for their work, which I did, and they say, well, we've moved on, I'm sorry, I can't give you that. And you're just like, well, I don't think you really did it. And you see that a lot with the partial reconfiguration, because the control is so difficult. But this is what we did for this work, and the way, I don't talk about in this type, but the way we're looking at doing now is doing just a small, medium, and large, just three different sizes. And it matches well with the various things. Like Viterbi, on the receive side, Viterbi is another large thing to do. And so Viterbi, we're hoping, will fit in the transform size as well. But we completed this and we tested it. And the way you have to do it, like I was saying, with whether using a bus or whether using any kind of interconnect, is you have to disable the tile, because the control bits, well, every bit coming out of that you have, you say this is going to come out of the partial reconfigurable side and go to the static circuit. They all toggle. They go like mad while you're reconfiguring it. But you disable the tile, you put it into reset, and then you don't look at the control signals. You reconfigure it. There's two ways of doing it. We use on-chip reconfiguration. I'll talk about going off-chip later. And then you enable the tile. And once you enable the tile, what's that mean? Once you enable the tile, samples just continue to flow. And what's important for us, I think, is the latency involved in this. And currently, we can reconfigure all the components of the transmitter, and it's I say approximately fast, because it's approximately 1 millisecond for the transform block. The modulation scheme is extremely quick to do, just microseconds. But as we were talking about earlier, this limits the frequency of reconfigurations possible, which is a challenge for cognitive radio tasks, where you want to switch on a very small granularity. And I don't know if we'll have time to address this in this project or not, but we looked at prefetching. There's a lot of runtime FPGA systems that do a lot of prefetching and hand in hand with speculative execution. If you have more tiles, you can drop on things while it's running, which is really good for our network on chip. The way we have it set up, it uses virtual table addressing. So you can just change the virtual tables and start routing samples through another block. And so kind of do some double buffering almost of tiles. And also currently the scheduling and the reconfiguration is done on chip. And so the last part, which I'll be doing hopefully soon, is moving that aspect off chip, which is bad because it'll limit how fast we can do. The transform will take a lot longer to reconfigure, but it'll be easier because it'll be on a nice general purpose processor, and we can dedicate more resources on the FPGA to actual doing work and not doing the control. So that's the flowchart again, is kind of what I've talked about so far is the network on chip, the operating system attached to it, the transmitter example all being done. And then just looking at, with the receiver, I would love to say it's done, but we still need to work on a little bit more. And then I'll take it and partition it over the network on chip, and I know how to do that. But it's the receiver is much more interesting than the transmitter. And then that'll be, I believe that'll be the end of the funding for the project as well.
So what is the role of the operating system? What's in the target?
The operating system is to schedule things, and it will do the reconfiguration steps as well. You're right. I mean, the scheduling it's not static in as much as you put on the modulation scheme you want, and then there's a control up to the scheduler to do something to swap it out, or maybe to schedule to a different port, or various things. It does various work to manage the network on chip.
So it's more like a management layer.
It is. It really is. You're right.
Get into the data path or something.
No. Yeah, you're absolutely correct that it gets into the data path, only that it has to stop the data path to do a reconfiguration almost. But you're correct. It's not a full-blown operating system.
So when you reconfigure, you essentially shut down the system.
You have to shut down the samples going in, so it definitely shuts down the pipeline of a transmitter. With the Viterbi one, though, I believe the way we'll do it is this is what I've done with networking steps, is the speculative execution, drop on all the possibility of how it would be handled, how the Viterbi paths would go, and then kind of shut down the paths that don't work. And so that's, I say that and it sounds great and easy. I haven't done it yet, but that's what we're hoping. And that's what I've done with my networking stuff in the past. Is there a question?
To 11, so what exactly do you
Oh,
Design,
in that one, we did the modulation scheme and we did the transform just to do various tap sizes.
But that can be a program. You can have a single hardware that can be programmed, right?
Exactly. And
So why would you reconfigure for that purpose?
well, it would be that, let's say, for example, that I can't fit both transforms on the FPGA because of the size constraints. So I can only fit one on there, but then all of a sudden the medium gets very noisy and I need a better more tap filter to use. Or I'm sorry, not filter, I keep saying, but a better transform or various things coming in. Or, there's some where some of the Viterbi's are faster, various things, and I'll talk about with everything we have on there now with the transmitter and the receiver, just standalone, it's 85% of the chip. And so it's one of those examples where I can't fit too much more on there. So these, if I do want to put, a different modulation scheme, modulation's a terrible example because it's so small, but if I want, let's say it was bigger, I would have to swap it out on the fly. And again, it comes to virtualizing the FPGA, making it software-defined radio. You really do need to virtualize the resources. But yeah, no, that's an excellent point, though. I mean, some of those examples, it's only the transform that's really big enough to worry about because it is huge. So, like I said, the need is receiver onto the NOC. We're going to move the schedule and the partial reconfiguration off chip for the reasons I've talked about. Just bitstreams take up memory sources, and eventually that gets to the virtualization problem. Large bitstreams will, for the entire chip, maybe can be a megabyte. Small ones can be 40 to 50 kilobytes. But the typical way you do it is you have a file system for reading bitstreams, which typically is done using a flash card, and that just puts another constraint on your actual FPGA system, which is not a great idea, but it works well for our extreme DSP board and various things. And the receiver transmitter take up 85% of the resources on our platform. And of course, it's one of those things, FPGA scale, they should get bigger, you should see bigger parts. But the challenge of virtualizing an FPGA is really still worth tackling. You could always say scaling for anything, but people will find reasons to fill it up. And it's just work in progress. So, hopefully in spring of 2008, we'll have more on the general purpose processor, working with GNU Radio people right now, and there's a group in Dublin that working with a little bit on that as well because they have some good GNU Radio people. Methodology for exploring it as opposed to simulation. And the thing being, you say it's a good idea to move to hardware, but then again, the reconfiguration step may make it not worthwhile. So decisions like that, there's a lot of ways to go. And just, again, looking at the partial reconfiguration cost and feasibility specifically for software-defined radio.
How scalable is this partial reconfiguration?
Scalable to...
In terms of, like, you are just changing taps on a filter now, but if you need to do something more complex function of FPGA, does that change anything in the timing of the reconfiguration?
No, I mean, it's very much like... it's analogous to a context switch, depending on how much state you have, and I convert, we think of a context switch depends on how much state you have to store off. This is how much state you have to replace. And so it's the same process regardless of what you're doing. The timing only matters in the size of the reconfiguration. So it scales.
The dial size?
Yes. So the actual percentage of the chip, and that's how it scales. And it's designed, we can talk about it after. It's just that's how it scales. There's nothing else. Everything else is the same. You feed through the same interface, and it just takes you as big as the chip is, as big as the region. There's no other complexity to it. So I'm nearing the end of the talk. Just 2 more slides. There's many components to this project. Again. One of the goals of this particular software-defined radio platform was using open source in such a way that people can actually buy this in a research group for maybe $5,000 to start up a research project on it which has been a challenge because there's things we wanted to buy. There's Xilinx IP we wanted to use, but we avoided it if possible. But there's custom IP, there's operating system work. Again, with those goals to isolate the components, leading to easier adoption of the platform. I think everyone agrees that FPGAs can provide the performance, but it's what we're striving to do, and I guess me specifically, is working to provide the configurability that's necessary so that non-FPGA designers can actually use these parts. So, well, thank you for listening, and I'll take questions if there's time.